Hi, it's Anthony again, and today we're going to try to get a better understanding of the idea of expectation in statistics. The reason we're covering this is I've found it kind of confusing, and in my efforts to kind of sort out my own understanding, I've learned a few things and I want to communicate that to other people, and at the very least also help me better understand the idea of expectation by working through a few examples as well. So the idea is we're going to first generate some random points using NumPy in order to generate from a statistical distribution, i.e. the Gaussian distribution is what we're going to use actually. And then we're going to also look at a symbolic way of thinking about expectation using SymPy, which I talked about in my last video. And when we put these two together, hopefully we can kind of see the overlap between like a numerical approach and more a symbolic approach or a like equation approach that you might see in a paper. Because sometimes there's a little bit of a disconnect between, like what does something actually mean when I'm reading it in a paper? Like what would that actually mean in code? So first we're going to take the numeric approach. So let's go ahead and get started. Okay, first we imported our libraries. We said we wanted 2,000 points. Then I used the NumPy random standard norm function in order to draw this number of points, 2,000, from a Gaussian probability density function, which is the normal distribution. So then these values are put into this function, this array of values, and then I just ran or plotted a histogram of the frequency at which they occur. And you can see this does look generally like a normal distribution, which is good, so it's supposed to. So now we need to move on to the idea of like what is expectation. So expectation is the probability of a particular value times the value evaluated through some function. So let me just write that out real quick. Okay, so expectation is E equals G of X times F of X. We're saying G is the probability that we're going to have a particular X. Then F is just evaluating the X at that particular value. So we can see maybe in this first graph right here, if I look at, let's say, -1, actually, yeah, -1, we can get an idea, out of 2,000 points, I'm going to get, around like 30 of them. And then let's say we have some function, and we're going to call it just x squared. So now our expectation at the value 30, or sorry, at the value of -1, okay, it's going to be, okay, so at -1, our probability of having that value is going to be 30, somewhere around 30, divided by the number of points, because we sampled 2,000 points. And then we evaluate the function at that particular value, -1. And we see that the expectation at -1 is about 0.015. So again, we just have the probability of a particular value. So this is the probability of -1 is somewhere around here. And then multiplying that value by some function in order to get our expectation. So this is definitely interesting, but normally when we look at expectations, we're like integrating over a whole probability. So let's take a quick look at how we might be able to do that. Okay, so here I'm saying take all my values, so all these values right here, actually it's more of in this range, and then multiply, or take each value and pass it through my function, which is going to be just x squared. Then, in order to get an idea of the frequency of this, I'm just going to take the mean, and I see that I get a mean of around 1. So what that's saying is that, for every value, I'm taking its probability more basically, and then multiplying that by this value, or by the function I would get here, or by the value I'd get by evaluating this function and then taking the mean. And when I integrate that all together, or I sum overall, I get that this is the expectation of this entire probability density function times this particular function. So you can see I get it around 1. Now let's take a look at what would happen if I just, instead of using this function, I use something like the absolute value. Okay, so this new function, instead of being x squared, it's just the absolute value of x, and you can see that the expectation I'm getting is 0.8, like 1. And we'll see in a minute if that's right, but this is interesting. We can just use different functions. Finally, let's just try what happens when you do the identity function. See what type of value we get. Okay, so you can see that when I just use the identity function, whatever x is, that's what I'm going to return it. I get something small, 0.17. It's pretty close to 0. It's a question, should it be 0 or not? We can, interestingly, if I just like run all my cells again, we can maybe get a better idea of what's going on if we just watch it a few times, or if we want to be a little more scientific, we could like set this in a loop. But running it a few times could probably give you a pretty good idea of what's going on. So you'll notice that like this value is below 1 a few times. Now it's above 1. This is about 0.8. It was below 0.8 a few times. Now it's above 0.8. This was above 0. Now it's below 0. So this is all pretty interesting. But what is it actually? Like, can we maybe more scientifically evaluate this? And we can't. So the way that we're going to do that is using SymPy. We're going to actually look at some of the math that we can use to evaluate these expectations using formulas rather than just sampling a lot of points. So let's try it. Okay, so I set up a symbolic function which will give me the Gaussian distribution. So if I just do a Google search for Gaussian or normal distribution, you can see this is the formula right here. This probability density function, and if I typed it all out correctly, then then this is what it is. So the mu here is the mean, the sigma is the standard deviation, and you can see I get this formula right here. So now what I want to do is just try to make sure we're doing what we think we are by doing a quick plot. So I imported the SymPy plotting right here, and let's see what happens when we actually go to plot this. We can plot from like -3 to 3. Oh, it looks like I did something wrong. That is not right. All right, let's see if we can figure it out. Okay, so that's looking a lot more like what we would expect. So I was missing a minus sign right here, and that solved the problem. So this is my Gaussian distribution. So the question then is, when we came up with these, we evaluated the expectation up here, and can we do something similar down here using a symbolic representation or like an equation type format? And the answer is yes, we can. So let's try the simplest case, which was just doing the identity function, and see what we get. So the identity function would be, let's call this fn, it would just be y. So that's the probability of a particular x, and then we want to get the value at that x. So we just multiply them together, and that is basically what we did right here. So if I evaluate this, then let's see what happens. So when I talk about evaluate, I'm saying I'm going to integrate over all possible values. So we want to make this go from negative infinity to positive infinity. And this n right here just says evaluate it numerically. If I take it out, so let's do it without it first. Okay, so it gives me a value of 0. So this is interesting. If we look back at the value we got here, we got we ran this a few times. We can run it again, and each time we run it, we're getting a really small number that's near 0. So the fact that this evaluates directly to 0 is interesting. It seems to indicate that we got the right value, and that's good. So we can also maybe get an idea of like how many points, how the number of points that we choose is going to influence the result. So if I change it to something small and then do run all, I'm getting something quite a bit different. 0.07, that's pretty high. At the same time, if I bump this up to like 5,000 and then run it, that's going to probably be closer to 0. Yeah, 0.006, even closer to 0 than we had before. And, obviously because this is a symbolic representation, it's evaluating directly to 0. So that's the identity function. Let's try our other functions. So we tried y times the absolute value of x. When I integrate that, let's see what we get. Okay, so I integrated it. I put this n in front of it, which just means numerically evaluate it. You can see we got 0.79. If we look back at the values we got for this NumPy version, we got 0.792. So that would seem to indicate that they're, that it aligns pretty well, which is good. So finally, we want to do this function that we had. We called my function up here, where we just squared it. So let's try that one. So when we run this function and get our expectation, we're getting an exact value of 1. So this is pretty interesting. If we look at our numeric version, we got 0.98. We've run this a few times now, and each time we get something similar. Here we're getting 0.9989, so it's very close to 1. And our mathematical equation formula is telling us it should be exactly 1. So this is pretty helpful to actually see the two different approaches. One using a symbolic approach and the other using like a sampling approach. And we should be getting similar values for both. So I hope that was helpful. That really helped me think through some of the ideas. And thank you for watching.